Good morning. So we will continue with today's lecture from where we were stopped in the last class. I understand and also I looked at back again our recorded video lecture. It was struck in between and maybe around 22 minutes after that it was audio only was able to be heard, not the slides. So I'm just going to start from the point where it was stuck and then I'll continue today's class. So in the last class, we essentially started with class and objective, understanding what is called a logarithmic decrement and energy dissipated in viscous damping, right? So before that class, we were just to learn about the damping properties and damping is necessary for dissipation of energy in a vibratory system and so on. And the damping can be classified as viscous damping, dry friction damping, or material or hysteresis damping it is called. This is all we studied. And last class we just started with damped free vibration of the system, where the governing equation of that is represented by mx double dot plus Ex dot plus Kx equal to 0. And the solution of that can be of any of these three forms. And here essentially we were able to represent our all vibrational classification that you have seen in one picture that's called state space diagram or phasor diagram. So that's going to be representing the variation of velocity vector as function of displacement vector. And here we finished, and then we just started to look at all the responses of these different classes in one picture, where we could see differentiate periodic motion and aperiodic motion. So periodic motion is what is a vibratory motion. So for a periodic motion, we should have either the damping is not present in the system. We should make an assumption that system is conservative. And such cases, you would have your response would have varying between fixed amplitudes like this. And in case there is a damping present and you are accounting the damping, and then you see that oscillation amplitude is decreasing gradually and it will reach to 0 at a point of time. And that vibration is what is called underdamped vibration, where you see zeta value, what we defined as the damping coefficient, ratio of damping coefficient to that of critical damping coefficient. So this is what we defined what is zeta as, and zeta value is between 0 and 1. You have a vibratory oscillatory motion that's called underdamped system. That's what we were essentially looking at. And you can also have different case when zeta is equal to 1, what would happen, and zeta is greater than 1, what would happen. That become an aperiodic motion. You could see the response of them. One is quickly settling to 0, another one is taking longer time to settle to 0. So the one quickly settling to 0 is got a lot of design applications where the damping is purposely introduced, that the oscillation is arrested and that motion is become aperiodic and quickly settling down. So such an example is what is that in gun barrel that we discussed. So with this, we were to continue with understanding what is logarithmic decrement. I explained, I have written down all the equations, but it was not recorded properly. So we will just to quickly go through them and then get into today's class. So this is that in particular underdamped response, underdamped vibrations, free vibration response is what is plotted in this graph. You could see that is varying and it is decreasing to approaching to 0 value. So here the response is function of the angular displacement. And you see any point of time t1, you can look at an amplitude x1, and another t2, you can look at an amplitude x2, and t1 to t2 is what is referring to a period of oscillation, tau d, that's 2 pi by omega d. And here, of course, you know omega d is damped circular frequency, damped circular, natural circular frequency, because free vibration. So it's called damped natural circular frequency. And there is a relationship between this omega d and omega n that we have already seen. So omega d is given by omega n times under root of 1 minus zeta square. So this is all we know in our mind, and we look at it. So here this something called a logarithmic decrement is quite useful parameter that is used to find out damping present in the system in case we do not know what is the damping in the system. Experimentally, we can find out. That's why we define this logarithmic decrement as natural logarithm of amplitude ratios of successive amplitude ratios. So x1 by x2. So x1 is at t1 and the end of the cycle x2. So successive amplitude ratios natural logarithm is what is defining logarithmic decrement. So that can be easily derived further, where I consider t1 my response is I'm taking this response. So that's going to be x e raised to zeta omega in t1 cos omega d dt1 minus 5. And at time t2, time t2, what is the angular displacement? Omega d t2 is what is angular displacement. So omega d into t1 plus tau d. So it is t1 plus this period of one complete cycle is what is added here. That's t2. So this is t2. So t2 is t1 plus tau d. If I put, I would be able to get that is nothing but t1 plus 2 pi radians angular displacement is what is omega. Angular displacement. So by substituting this T2 here, and I would be able to see that the value of cos at one cycle and the next cycle incremented by 2 pi would be same. So that disappears. So I'll have my ratios defined by this. And then I take them top, then I see that it is further. And finally, I'm able to define my logarithmic decrement is product of damping ratio, natural frequency into time period of damped oscillation. So that gives me further to look at what is the, say further we substitute for tau d and then it reduces to this. So I'm able to express my logarithmic decrement as function of zeta. So zeta is very, very small for lightly damped structure. Like the structure, steel panels and so on, if you see in an automobile, that's very lightly damped compared to that of another element in an automobile, tire, rubber. So very lightly damped structure, zeta value is very, very small. So if this is going to be 0, then I would have 2 pi zeta is approximately. So multiply damping ratio with this will be equal to logarithmic decrement. Logarithmic decrement, something that we can experimentally find out. And I divide that by 2 pi, I'll be able to know what is the system damping from damping ratio. That's the reason why we are to understand this definition of logarithmic decrement. And you can express now damping ratio as function of logarithmic decrement with respect to this smaller manipulation. Square both sides and then rearrange the term. So get your expression for zeta in function of logarithmic decrement. And it is also that not necessarily you should measure during vibration successive amplitude. You can also measure for some m cycle and then you can find out this logarithmic decrement value. That's what you would see that further manipulation. I write instead of x1 by x2, x1 by xm plus 1. So after m cycle. So you see then I can write the ratios x1 by x2, x2 by x3 and so on like this. And generally at any jth and j plus 1th amplitude ratio is what is defining my logarithmic decrement, and that is what is given by this that we have seen. So if it is for L xm by xm plus 1, it is L xm by L xm 1 is what is going to be this. So you can see here, this is not m, this is 1, right? X1 by xm plus 1 is going to be this. So you can again look at, since it is natural log exponential power, this is going to be this value straight away on this side. So I bring 1 by m here, I have it on my right hand side. This what is just now we defined as logarithmic decrement. So logarithmic decrement can be obtained by any particular time t, what is its amplitude, and after m cycles completes, what is the amplitude if I have, I can find the ratio and take natural logarithm and divide that by number of cycles, and that would give me straight away my logarithmic decrement value, so that I can find out what is the damping present in my structure. So you have a component given to you, you have experimentally able to measure number of oscillations. So do an experiment and find the number of oscillation and first oscillations beginning, you find the amplitude of mth oscillation, find the amplitude. You know what is the damping of your system by getting C by Cc value, zeta value. So that is the advantage of this definition. So this is what I was explaining, writing down, but you are not able to look at it at that point of time. I think it is solved now. You would understand better now. So another part of the last lecture objective was to understand what is dissipation in viscously damped vibration. So energy dissipated in viscous damping damper. So for that, we know that in any damped system, the rate of change of energy with respect to time, dW by dt, is given by force into velocity. Where in the case of damping, the force is damping force, that is CV, minus sign is always this force is against that of velocity. That's why this minus. So if I add and I get this, and now for this term minuses, that shows the dissipation energy, the energy getting dissipated. So this is my expression of rate of change of energy with respect to time, and that would help me further to find out. So in a simple harmonic motion, you see x of t is x sine omega dt. So this can be considered as a solution, any harmonic function. And you may ask a question that how can we have energy dissipated and a damped vibration stops in a free vibration. In forced vibration only you can make all the time the vibration continue with the excitation frequency, say. In such cases, with the excitation frequency of omega d, the forced vibration, the loss of energy due to damping is supplied by excitation in steady state to forced vibration. We are going to understand this all as we are going to look at forced vibration. So any structure which is damped and I give an excitation, that means giving some initial disturbance, and it is freely going to oscillate and stop, die out. And that is the nature of damped free vibration. But I want to make that structure to ever vibrate with a decided frequency of my interest. Then what will I do? I will excite that structure. Instead of disturbing it, I will apply a sinusoidal wave. That is x sine omega t. So when I apply that, what will happen? You would have your structure will be continuously vibrating, but the system has got damping. The damping will dissipate energy. So the energy dissipation is supplied by this excitation in steady state forced vibration. So let's look at now how do you find out that dissipated energy in a particular cycle. So energy dissipated in one complete cycle would be now given from this. So if this is my response of a steady state response of forced vibration, right? We have not started with the forced vibration. We're going to do that today, but consider that's a forced vibration. And then its velocity derivative gives you this. So you can substitute in this place and carry out the simple integration with this understanding of trigonometric relation, and you would be able to integrate and finally get the change dissipated energy as pi into damping coefficient times omega d into x squared. So this is what is energy dissipated per cycle, and it is proportional to see the amplitude square. Also, you have to note that it is also proportional. It is also been depending on the values of zeta and omega d. So if I say the energy dissipated for the given values of damping and amplitude, that is x and c value, is it fixed? No, it is also going to depend on what is this excitation frequency, that we should be always remembering in mind. So if we have understood this expression, this is very much essential in solving problems. What is the energy that is dissipated during damped vibration? It's asked. You should be able to use this formula to find out. And you see, additionally, there are two more important definitions called the specific damping capacity. So that's nothing but the fraction of total energy per cycle lost. The fraction of total energy per cycle. So delta W by total energy. So the total energy of the system, maximum energy can be given either by potential energy or maximum kinetic energy. Right? So maximum potential energy would be at the extreme of its point of reversal. It will be, and maximum potential energy at its static equilibrium position. So if you have this, and this energy is what is equal. So if you equate, you could define omega n is under root of k by m, or I'm going to use now this kinetic energy expression here as the total energy available, and I'm going to look at it. This ratio eliminates some of the terms, and finally it comes out to be 2 times the logarithmic decrement. So it is 4 pi into zeta. Why? Because I just manipulate this term 2 pi c by this as 2 into 2 pi by omega d and c by 2m. So same as this. And 2 pi by omega d is time period of damped oscillation and c by 2m is nothing but zeta omega n. So you would be able to have such relationship which is constant. So the fraction of total energy per cycle gone is fraction constant if you know the zeta of that, and zeta to find out you have logarithmic decrement and so on. And there's something called the loss coefficient. The ratio of energy dissipated per radiance per total strain energy is what is defining loss coefficient. So these all terms are necessary to remember all the time when you have to answer some competitive exam questions. So this is what the intention was to complete in the last class. Since the support of network was poor, it is completed today. So let's start today's class with damped forced vibration, right? So this is lecture number 8, and today's date is 18/08/2021. And what is that lecture topic is forced damped vibration, right? So forced damped vibration. So if you are very keenly learning from the beginning of my lecture, you would ask why suddenly I go to damped? Why don't we start with undamped system? So undamped system is the simplified and damped system. So let us look at this general aspect, then we will reduce to undamped system means what it would be. So that would save our time. And that's why I straight away going into damped forced vibration. So when you say forced vibration, it is different from free vibration. Free vibration is excited in a structure by just disturbing its initial conditions. That is what is the fundamental that we learned. And forced vibration is something that you are forcing the system to vibrate. You are rotating a shaft at a particular speed. That means you are exciting the shaft with that of rotational speed, that frequency. But the shaft can have its own natural frequency. If your excitation frequency matches with the shaft natural frequency of your material, then something called a resonance will occur that we need to prevent. So forced damped vibration is inevitable in any of the mechanical system in power transmission. That's for an example. So a shaft rotating at a particular speed is an example, classical example of harmonically excited forced damped vibration. So when I say harmonically excited, so this is a specific case for forced damped vibration for harmonic excitation. This is what we are going to see. That means you can also have other excitation function and you can look at the response. So the excitation function can be deterministic like this case, or it can also be random case. For an example, the excitation that comes to the tire and road interaction of our vehicle in our course we are going to study is not harmonic excitation purely. It is random excitation. So there are methodologies to account the random excitation and the vibration response. That is what we will be learning in our vehicle dynamics course in vertical dynamics part. Make a note of this point. So now what we do is again a fundamental, and we go for a simplified excitation force called a harmonic excitation force. When I say harmonic excitation force, what is that? You would remember maybe F naught would be some magnitude time. F is equal to F of t. So look at F of t, maybe some amplitude F naught time cos omega t. So if I write that, that's a harmonic excitation, or sine omega t, if I write, that's a harmonic excitation. So I'm going to consider this as my force that is going to act on a vibratory system and create the vibration continuing because of this excitation. So now look at our vibration system. We have an important element, a spring, and we have an important element, a damper. And these two are connected to mass M. So this is K and this is C. And now you see this is settled at its static equilibrium position or stable equilibrium point. And from here I'm going to give this F of t. From here I'm going to give this F of t. Right. So when I give this excitation F of t, I can get my governing equation simple. So I have here two forces, that is K x and Cx dot, and that's going to be equal to, and of course there is a force Ft, forcing function, and I will have that's equal to mx double dot. So this is what is my application of Newton's law. So I have on left hand side free body diagram, on right hand side kinetic diagram in fundamental science. Engineering mechanics, we have learned that. So writing down the convention down positive, I would have minus kx minus cx dot minus plus f of t equals mx double dot. So grouping on one side other than the force, the external force, is going to be mx double dot plus cx dot plus kx equals f of t. So this is my governing equation. So look at the governing equation is simply equated to the excitation force function. If this is 0, then it is damped free vibration. So it is f of t, so it is forced damped vibration. And this forcing function again further classify, is it an harmonic excitation, or is it some step input excitation, or is it an impulse excitation, or it is a random excitation, and so on. So today's class we are going to look at this vibration is caused by f of t equals f naught cos omega nt, right? So if that is so, and we know that popular, see when you solve this, what is this equation? It is second order ordinary non-homogeneous equation, because right hand side of that is not equal to 0. So this type of the differential equation solution would have a response would be of two kind. One is x of t, and that is called transient response or complementary function, plus steady state response xt of t. Sometimes it is called p, or particular integral or complementary integral part solution. So this is what is called impulse response or a transient response. This is what is called a steady state response. So both will be the solution of this. So let's look at what is this. It's a transient response. What is this? Is called steady state response. So the steady state response is what is going to be vibrating with the frequency same as that of excitation frequency. So what is my excitation frequency? F of t is equal to f naught cos omega t when I put. So this is omega simply is what is excitation frequency. So with the excitation frequency, this would be vibrating. So this is actually going to be my solution after the smallest time period. So when you have a system forcefully vibrated like that, this transient, the name transient is not for a long time. It is going to die out immediately. So the transient vibration is going to be 0. So how do you get this transient response? So how to get this transient response is simply making right hand side 0. So mx double dot plus cx dot plus kx equating to 0 is what is the governing equation of transient response. What we have studied, nothing but the free damped vibration. So the steady state response is going to be given by the response with this frequency. So the response of this frequency, you could have seen that with the natural damped free vibration, right? With the omega d, we had a response. We looked at that so far. And this is the response. So this first you should understand. So we will have addition of these two is what is going to be my total response of the force response system. But however, I would ignore this transient responses thing in a functional aspect of vibration, and I would make my system to vibrate with the steady state response. So what is that is important in vehicle dynamics is always we look for steady state response. That is its characteristics. So we drive our vehicle with the cruising speed. We don't have any transient response there. There won't be any local vibrations. Like that, all you would see in handling vehicle lateral dynamics, we see that you would have both, and you don't want transient response present in your vehicle. You want only steady state response every time. So now you learn this and you connect this at that time of learning, and particularly lateral dynamics. So what am I going to do is I'm going to start with what you have learned and known to you. All right. So I have my governing equation mx double dot plus cx dot plus kx equals 0. Equals now f naught cos omega t. So this is my governing equation. And I'm going to consider the response of this as one of my known part. That is, I'm going to consider what the response of a steady state response. So xp of t is particular integral part mathematically, and that's called the steady state response. And that's going to be x cos, look at here, omega I'm writing, not omega t, omega t minus phi. So this is my general solution. I can also have xp of t as x naught sine omega t plus phi, or I can also have a combination of sine and cosine. I can also represent my response as exponential to st, like a Laplace variable. I can also represent as x e raised to I omega t and so on. Very way you can represent this harmonic excitation. So I'm taking a case of this, which we are familiar with just now. In the last class also we have taken this. So if this is so, I would first get my derivatives xp of t. So you understand why do I find out derivative? I'm going to substitute this all in this to get the response. So if I do that, it's going to be minus x omega sine omega t minus phi, and x double dot p is going to be minus x omega squared cos omega t minus phi. All right. So substituting this all in equation 1. So put in 1. What is that I'm going to get? I'm going to have m, this is going to be m into minus x omega squared cos omega t minus phi plus c into minus x omega sine omega t minus phi plus k into x cos omega t minus phi. And that's what is equal to f naught cos omega t x naught cos omega t. So what am I going to do is now, so look at in this, I'm going to group the terms, right? I'm going to I'm going to group the terms. So you look at this term and this term. I have cos omega t minus phi common. I have here cos omega t minus phi. I have cos omega t minus phi. So let me write now this equation as taking x is common in all, taking that out, and I'm going to rewrite now this positive term. So k minus x omega m omega square into cos omega t minus phi. And then I have this term. So here you have this minus. So it's minus c omega sine omega t minus phi. Just to have written like this now. On the other side, I have f naught cos omega t. So now we know our well-known trigonometric relationship. What is that? I know what is cos a minus b, what is sin a minus b. So cos omega t minus phi can be cos a cos b minus plus sin a sin b. So it's going to be cos omega t cos phi plus sin omega t sin phi, right? And similarly, sin omega t minus phi is sin a cos b minus cos a sin b. So sin omega t cos phi minus cos omega t sin phi, right? This is our trigonometric formulas. So using this, I can expand now this equation, and that's going to give a very interesting set of equations. So let me substitute now, expand this here and this, and then reduce my equation further. So that's going to be x into k minus m omega square into, so this is going to be cos omega t cos phi plus sine omega t sine phi minus c omega into sine omega t cos phi minus cos omega t sine phi. And that's what is equal to f naught. I'm just going to write this f naught cos omega t plus I just deliberately put here 0 f naught. Instead of f naught, I put 0 amplitude there, right? So 0 sine omega t sine phi 0 sine phi. So this 0 sine phi I just deliberately put so that now this equation would be expressed as omega t term separately, phi term separately, right? So this is going to further help me out to rewrite my equation like this. So that equations are x into this amplitude into I have k minus m omega square. Here see I'm going to group what omega t terms. So cos phi is coefficient of omega t I'm going to write. So here I have to have cos phi, right? And also I have here sine omega t terms. See, I'm just doing that so that I will have here cos omega t coefficient and sine phi coefficients. So this is not sine phi, sine omega t. Correct this here. I'm writing it as not in terms of phi. That's going to be sine omega t. So I'm going to write on side the coefficient of cos omega t, coefficient of sine omega t. So coefficient of cos omega t is this, coefficient of sine omega t is this into sine phi. So that's going to be this into, right? So that's going to be minus of minus plus, minus of minus plus, and c omega sine phi, and that's what is equal to f naught, its coefficient. And sine omega t coefficients, this. So again, I'll have x into k minus m omega square into sine phi. And here sine omega t coefficient is this minus c omega cos phi. And on the other side, the sine omega t coefficient is 0. So this two set of equation I get. So now, what is the objective I'm doing is I want to eliminate this phase angle from this. That's what I'm doing. Phi is the phase angle, and I want to eliminate this phase angle. So how do you understand phi is the phase angle? Look at here, my response is having cos omega t minus phi, whereas my forcing function excitation is omega t. And since it is minus, my response lag my excitation force by phi angle. That's the phase angle. So we will represent it vectorially and you will understand. So my forcing function is exciting with the omega t, whereas my response is lagging my excitation angular displacement by phi angle. So that is what is this phi here we look at. And I want to eliminate and get my expression. And what I can do that squaring both sides and adding. That would eliminate because I have here cos phi, sin phi, here sin phi, cos phi opposite. So if I square on both sides and here plus minus, so it is very simple. So you know that we have used this many a time in mechanics. You could have used this to represent your principal moment of inertia to find out you have done such kind of manipulation. So if I do that, I would finally end up with this. What is that? I would have x square, because square, x square, within bracket, I have k minus m omega square whole square. And I will have a term cos squared phi plus sin squared phi. I'm just writing it and that eliminates to show. And c omega whole square and within bracket sin squared phi plus cos squared phi. And on the other side, it's going to be f naught square. So see, this is 1 and this is 1. And that goes, so I will have x squared into k minus m omega square whole square plus c omega whole square. On the other side, it is f naught square. So now f naught cos omega t, in this expression is f naught, that amplitude only is appearing. So what is my amplitude now? So that would be equal to, so I bring it down here and take a square root. So this is going to be f naught by under root of k minus m omega square whole square plus c omega whole square. C omega whole square. So this is my amplitude now. This is my amplitude. And what is my phase angle? So that is phi, that's equal to tan inverse of C omega by K minus M omega square. M omega square. That's my phase angle. So I have my phase angle here in terms of parameters of my system. I know damping coefficient, I know K, I know mass, I know what is phase angle, by which the response would lag than the excitation frequency. So I would be able to get the amplitude of vibration due to this forced vibration, harmonic excitation, right? So this is what on one hand that we have. What is, by the way, the response? The response is say xp of t, steady state response, xp of t. I have not looked at transient response at the moment. I am looking at steady state response. That would be x cos omega t minus phi. So in this you have x, you have phi given by this, right? So just let me represent this vectors in a graphical as well as vectorial presentation that would again appeal to you to just to remember this thing nicely, right? Just a minute, I do that. I'm going to take now. I'm going to represent to you this. And let us get all in one go. So how this response is going to be? It's going to be like this. So look at now this response. It's gone out of the picture. Yeah. Is it visible now? Right. So look at here now. I have my graphical representation of this forced damped vibration. Forced damped vibration. And you see here the response is xp of t. Right. What be xp of t? xp of t is x cos omega t minus phi. And phi is what is phase angle, which is representing the response lagging than the forcing function by phi angle. So what is my f of t? F of t is f naught cos omega t. If the length of this vector is f naught cos omega t is what is projection on this vertical axis, right? So that is my function. So what is my forcing function? F of t is equal to f naught cos omega t. And response is x cos omega t minus phi. So this is what now graphically represented here, and omega is what is the excitation frequency, and that is why with that frequency both the vectors are rotating. Look at here, frequency is omega, here also frequency is omega, and they are different with their angular orientation by angle called phase angle. So phi is what is phase angle. Right. So we have looked at in simple harmonic motion, velocity vector, displacement vector, and acceleration vectors with their phase angles. That is correct. That is the representation of your harmonic motion, free vibration. But forced vibration, I have excitation also is a harmonic function, response also harmonic function. So that is what is this. So I have just plotted only xp of t. If I plot x dot of p, that would be phi angle, phi by 2, lead this, and x double dot of p, that will be pi angle than the displacement lead. Like that you would have that. That is not represented here, only displacement represented in the purpose. So the variation you can see here. So f of t at t is equal to 0, omega t is 0, so it is going to be f naught. So this value is f naught. This is f naught here. And your response is phi angle lags, so that comes like this. So your response here, you see, it is again not a damped vibration. This damping is present in the system, but your response is having your amplitude constant and it vibrate between that. That's what is happening. So you may ask now, what is happening to energy dissipation? Energy dissipation happens simultaneously, and then the energy is supplied by this forcing function. That is what is this. So the response is this, and the forcing function is this. So you would be able to understand this better. So now how do I represent vectorially? I take the reference is vertical in this case, and displacement vector is omega t minus phi. So this angle is omega t minus phi, where my x vector is there. We know spring is x times k. So your spring force is in this direction, and your velocity will be at 90 degrees, because velocity vector is 90 degrees leads the displacement vector. That is why c into omega x is represented like this. And then inertia vector leads the displacement by 180 degrees. That's why it is in this direction like that. And then you would be able to connect this vector, closing vector, that is your forcing vector. This is how your forced damped vibration is represented. Forced damped vibration due to f of t equals f naught cos omega t. That's all. So any doubt in this representation? You understood. So now let's just go and see very interesting aspects. I'm going to slightly manipulate and rewrite this equation. So I have x here, that's equal to f naught divided by, we just have seen k minus m omega square whole square plus c omega whole square under root. Correct? So this is what is my amplitude. So I'm going to divide numerator denominator by k. So if I divide that, it's going to be inside k square. It's going to be inside k square. So look at now what is f naught by k. So your vibratory system, when it is attached with the mass, it has come to a static equilibrium position. That is your static deflection. So this f naught is only force is applied, it's not harmonic, then it will take your mass to its static equilibrium position. That's what is going to be k into delta st. So this gives me f naught by k is nothing but delta st. So this term here is delta st. I bring that term on the other sides and have this as a ratio. So delta st. And this here, numerator x is called dynamic displacement. Denominator delta subscript st called static displacement. Dynamic displacement, static displacement. And this ratio is what is called magnification factor. Magnification factor. So this is an important factor that you have to understand in design of systems, right? That we're characterizing your system. So magnification factor is referred or defined as the ratio of dynamic displacement to that of static displacement. So this term is brought down. So I'll have here on the other side 1. And this you see interestingly, when I have this k square taken here inside, I can manipulate this in this fashion. So I'm just going to, this is already numerator, it is square term, right? And here it is this. So if I have to take this inside, that's going to be k. So this k gives off. So that's 1 minus m into omega squared by k within bracket this whole square. Plus here it's going to be c omega by k whole square. And it's all under radical. So this you see again interestingly 1 by, what is k by m? It is omega n. So I'm going to rewrite this as 1 minus omega by omega n whole square plus, and you see the c omega by k is nothing but 2 zeta omega by omega n. I can prove that now. So see now I am expressing my magnification factor in terms of excitation frequency, natural frequency of the system, and damping ratio, instead of explicit appearance of elements of your vibratory system, that is mass, damping coefficient, or k, stiffness of the value. I just take them out and I put it in this fashion, and that's going to give a non-dimensional kind of number. So there's no unit for this because it's displacement ratio. So I get this now here like this. So this all, why do we do is for a convenient form that we have. So let me define here a small letter r is nothing but this omega by omega n. So what is omega is excitation force frequency. Omega n is system natural frequency when damping is not considered. That's omega n. It's not omega d, it's omega n, right? So when I put that, I can rewrite this equation, right? If this is so, I can rewrite this equation as 1 by, so what is this? MF equals 1 by under root of 1 minus r squared whole square plus 2 zeta r whole square. So I leave it to you to just to get C omega by K is nothing but 2 zeta omega by omega n. See, it's simple. So what is this? C by K by m omega n. So C by omega n can be written as this form, 2 zeta omega n. That I leave it to you to just to find that relationship. And now we define what is this magnification factor, right? I just to finish it in another 2-3 minutes, and then we will see in the next class the characteristics with these equations. So for that, let me just see that if this is what is your forced damped vibration. So forced undamped vibration means what is that you require? You require damping ratio 0, right? So for the case of undamped system forced vibration, I was telling at the beginning, I don't take this as the starting point, rather I'm taking from here to the first point. If that is so, what is that is necessary? Damping is 0 in the system. So it is simply a spring alone with the mass and its static equilibrium and excited by f of t. F of t. So if that is so, here in this zeta is 0, so this term goes off. So I would have my x by delta st is going to be simply 1 by under root of 1 minus omega by omega n whole square. So that's my magnification factor in case of my underdamped system. You can also write an amplitude before we had this expression, right? This expression. So here what will happen? This term is going to be 0. So this is going to be rewritten as like this. So I can also have my magnification factor in terms of forcing function, amplitude, and the system parameters. So that's going to be f naught by k minus m omega square. So this is my sorry, this is not magnification factor, where amplitude. I'm writing this is amplitude. This is amplitude. This is amplitude. X would be equal to this. So if I divide this by k and divide by k, I get this form. And here it's going to be delta st that I bring in, I'll get this. So from this, I would say my amplitude of response is going to be only f naught k minus m omega square. Whereas in forced damped vibration, I had that other element comes into picture. That's what you have seen in this slide at the end. See here. So you have this element. So this goes off, and what is that is there left is this. So in this equation, what would happen? What would happen? See, when this term is 0, this is 0. So phi would be 0. So phase angle would be 0. So what would be my response? It is simply x cos omega t. That's all. That's going to be simply x cos omega t. So I'm just going to write now my response of that particular case. So what is happening, you understand, right? So x of p, xp of t for forced undamped vibration, your governing equation is going to be only mx double dot plus kx equal to f naught cos omega t. And xp of t would be equal to x cos omega t. Because phase angle is 0, damping is not there, that's making that 0, just now we have seen. And your response and your forcing function is the same, in phase with the system. And it can also go out of phase. That's what we have to see. So it can either be in phase or it can be in out of phase. So if that is so, you can have your xp dot of t. What is that? Is going to be x omega n. And it is undamped vibration. So it's free vibration. This frequency here is omega n. It is not forcing frequency. The response will be with the omega n. And this is so when this omega equals omega n, it's a particular case where you have resonance occurs. The amplitude goes to infinity. X is going to infinity. It's going to be infinity. Because damping is not present. So you can see interestingly how these graphs are appearing. I'm just finishing it in 1 minute. Omega n t and xp double dot of t will be minus x omega squared cos omega n t. You understand here why phi is not there? Omega nt minus phi is not there. It's clear. So this is what is my discussion point, and you can see that what would be your pre-vibration response. I just plot the response only to you now, and then end the lecture. That's going to be something like this. That's going to be something like this. So what is the plot for this case is, I take my magnification factor on vertical axis, and on a horizontal axis, if I have the ratio omega by omega n, for forced undamped vibration system, I would have my response something like this. So that's going to be something like this. So it will be from 1. This ratio is 1, 2, and so on. So from 1, it goes up like this. And this ratio can also be at a point 1. This is 0, 1, 2, and so on. It will increase, right? So when it is 1, you will see this shoots up here like this. And when it's omega is equal to omega n, it's going to infinity. And on the other side, you see, and it will be flipped from here. It will be like this. It will asymptotically reach there. So this point, when r is equal to 1, when r is equal to 1, you get this resonant point. When r is less than 1, you have here amplitude peaks up here in one direction. When r is greater than 1, it's coming from here like this. But as r going to be greater than 1, much greater than 1, what is happening to magnification factor? Magnification factor reaches to 0. Reaches to 0. That means there is no displacement. When it is 0, x is 0, amplitude becomes 0. That's the meaning. That is going to be asymptotically, right? So when omega is equal to omega n this state, so this is how your response would come. So how do you have to understand this here is this: when r is less than 1 or r is greater than 1. When r is less than 1, your forcing function and your response is in phase. So your forcing function is something cos function. So it will be like this, right? So this is f naught, and this is omega t. So you would have your function like this going, and your x of t also would be with a similar way. That also in phase. This is x of t, xp of t. Your steady state vibration also is like this. If r is greater than 1, the response will be out of phase. So this is for r less than 1. When r is greater than 1, that means the excitation frequency is much greater than that of the natural frequency of the system, and then you would have your response go out of phase. You would have your response like this. So it will start from minus here. So that is what you have to understand. So you give a forcing function like this, you would have your response 180 degree out of phase like this. In this case, your forcing function and your response is the same. That means your excitation frequency is lesser than the natural frequency of the system. But what is not preferred? Making these two meeting is not preferred. If these two are meeting, then you'll have an amplitude rises to infinity to lead to breakage of your system, non-functioning of your system. Why? Because there is no measure of damping. This is not damped system. That's one. Mathematically, what's happening to understand this is needed. But any time your system will have a damping sufficient enough so that you would have this peak amplitude not reaching to infinity, rather it would be at a finite value, where the material property would take care that fall below the yield point of your flexing, so and so on. That's the fundamental of design. So I stop at this point of time, and we will continue like that. Magnification factor, how does it vary as function of frequency ratios, omega by omega n? Similarly, the phase angle, another important physical property here. How does it vary as function of this for forced damped vibration, which you have learned today? That is the starting point for the next class. So I stop now. If you have any doubts, please ask. Otherwise, we will end the lecture. Any doubts? No doubts.